Welcome to today's explainer, Prometheus, and what senior engineers know that most developers absolutely don't. Look, today we're moving way past just shipping basic features. We're diving headfirst into the battle-tested realities of mastering large-scale production environments. Because honestly, what separates a junior coder from a senior backend engineer isn't just writing some clever algorithm. It's about how you build, how you observe, and how you protect your systems when reality hits them hard. And as you'll see, tools like Prometheus, they unlock the true observability you need to actually survive. Let's get right into it.
Picture this. It's Tuesday, maybe 10 a.m. You're getting these intermittent 502 bad gateway errors. Your Kubernetes pods are just continuously restarting. Of course, the dev team swears up and down they didn't deploy any new code, right? So you check the standard dashboards. Nothing. Absolutely nothing out of the ordinary. But here's the worst part. You run a command to check those crashed pods, and your logs are completely, utterly empty. No way to trace it. Your application is just dying in total silence.
Now, juniors might joke about the classic scream test. Shut off a server and wait to see who complains. But professionals know better. This silent death, it's the unmistakable signature of the Linux kernel's OM killer, the out-of-memory killer. See, the application isn't throwing a neat little Java or Node exception that gets safely scooped up by your logging pipeline. No, it is being violently terminated by the operating system right at the kernel level for crossing its strict memory boundaries.
So part 1, the silent production killers. Let's break down the immediate difference between how a novice reacts to an outage like this and how a seasoned senior investigates it.
When things break, the junior mindset usually just points fingers at recent code deployments. They're immediately looking for human error in the latest commit. But senior engineers, they formulate hypotheses based on actual system behavior. They're looking at node metrics, liveness probes, the container runtime execution. They actually build a mathematical dependency graph in their heads, mapping the exact network ingress path to the specific node resource pool, just to isolate the failure. They know that if pods are restarting, logs are empty, and the node itself is healthy, you don't blame the developer first. You suspect the kernel.
Moving on to Section 2, seniors delete more code. Look, if you actually want to survive these kinds of production outages, you have to embrace a pretty counterintuitive reality about system architecture. The developer who gets promoted isn't the one blindly adding 50,000 lines of code to the repo. It's the senior engineer who deletes 15,000 lines, rips out 3 entire microservices, and drops 2 dependencies. Seriously, a junior's contribution graph looks like a bunch of mountain peaks. A senior's, it looks like a valley.
You've got to internalize this fundamental truth. Every single line of code is a liability. Every clever abstraction, every redundant feature flag, every just-in-case validation layer, it literally all adds to the cognitive load of your team. Take, for example, a massive, unoptimized regex validation layer. You slap it onto every incoming JSON payload just in case some malformed data sneaks through. Well, under heavy load, that single regex can completely block the event loop. Bam! It instantly becomes a catastrophic production bottleneck. It just exponentially increases the surface area for failure across your distributed system.
So what do? We systematically eliminate that complexity. Delete redundant code logic. Purge those unused endpoints that literally only QA has ever touched. Remove the abandoned analytics dashboards that are secretly running super expensive database queries in the background. Ruthlessly kill premature optimizations built for these massive traffic spikes that, let's be real, never actually materialized. And drop heavy, bloated NPM packages when a simple native function would do the exact same job. Less code equals fewer bugs. In zero code, that's the only code that requires zero maintenance.
Which brings us to Section 3, taming the tail latency. Because once your code base is actually lean, you need to confront the lies your performance dashboards are telling you.
If you're only looking at that average latency bar, you are completely flying blind. Notice how average metrics totally hide the catastrophic edge cases. You're entirely ignoring the 1 in 100 users whose requests are just dragging your system into the dirt before network overhead even hits. Averages smooth out the harsh reality of the terrible user experiences happening right at the edges of your platform.
Optimizing for the 99th percentile, the P99 tail latency is absolutely crucial at scale. Why? Because in massive distributed systems, rare slow events just aren't rare anymore. Think about it. If 1 out of 100 requests takes 5 seconds and a single user's page load requires 100 concurrent asset requests, probability dictates that almost every single user will experience that 5-second delay.
Your best-case scenario suddenly becomes completely irrelevant.
So to tame this tail latency, follow this 5-step playbook. First, instrument explicit deadlines and budgets. Second, use off-CPU profiling to find out where your threads are actually just sitting there waiting. Third, collapse those synchronous network hops. Fourth, introduce tail controls like request hedging. That's where, if a response isn't received in a super aggressive timeframe, you immediately fire a redundant second request to race the first one. And finally, fifth, implement bulkheads. This physically isolates thread pools, so if your notification service fails, it doesn't consume the threads you desperately need for your checkout service.
Okay, Section 4. Distributed system nightmares. Even with amazing latency controls in place, the real world is eventually going to break your architecture. And honestly, it usually happens through totally predictable engineering mistakes.
These are the classic nightmares every senior engineer has sweat through at 3 a.m. Database connections leaking until the entire system just gives up and crashes. N+1 queries absolutely crushing your infrastructure under their own weight. The default deny network policy delusion, where the security team locks down a namespace so incredibly hard they instantly break core DNS routing. Feature flag coupling deadlocks, where flag A needs flag B to be evaluated, but both are blocking the exact same exhausted database connection. Oh, and asynchronous silent failures, where jobs just get stuck in queues forever without triggering a single alarm.
And all these nightmares inevitably compound into auto-scaling mistakes. Look, CPU is a terrible metric for auto-scaling modern web services. It's a lagging indicator. By the time your CPU is spiking, your queue is already backed up, your request threads are exhausted, and your latency is totally destroyed. The senior approach, auto-scaling based on concurrent in-flight requests, that is a leading indicator that preemptively scales your system to handle the load way before the CPU ever has a chance to spike. Next up, Section 5. Observability beyond basic monitoring. This leads us to a core transition every mid-level engineer has to make to reach that next level. And this is exactly where the true power of tools like Prometheus really shines. The mental model for basic monitoring is pretty simple, right? Measure known quantities, fire alerts when thresholds get crossed. Basically, monitoring tells you that something broke. But in a microservices architecture, you're going to face combinatorial, unknown failures that basic health checks will literally never catch. Observability is a whole different ballgame. Observability tells you why it broke. It lets you query the internal state of your system purely by looking at its external outputs.
You really have to stop monitoring the plumbing and start architecting for the payload. Think about it. It doesn't matter if your load balancer returns a perfectly healthy 200 OK status if your user is staring at a blank white search page. Semantic monitoring means tracking actual business logic value, things like search click-through rate or average items per cart. And this is exactly where Prometheus excels. It allows your application code to natively expose a /metrics endpoint that exports these highly specific, custom business metrics in real time.
Choosing the right stack to actually get this visibility is absolutely critical, and it really separates the novices from the veterans. SaaS tools like Datadog or New Relic, they offer incredible lightning-fast setups, if you have the budget for it. But at true enterprise scale, tracking every unique user ID or trace ID creates what we call high cardinality data. In a commercial pricing model where you're paying per custom metric or per gigabyte ingested, your observability bill will literally explode into the millions. No joke. This is exactly why Prometheus, specifically within the open-source Grafana LGTM stack, that's Loki, Grafana, Tempo, and Mimr, is the absolute weapon of choice for senior ops teams. Its pull-based scraping model handles high-cardinality data brilliantly, it gives you complete ownership of your data, and it totally insulates you from vendor lock-in.
Finally, Section 6. Architecting for inevitable failure. Because at the end of the day, no matter how perfect your observability stack is, you have to engineer your actual application code to survive the inevitable catastrophe.
Resilience isn't just an infrastructure feature, it is a core application requirement. You have to use back pressure to tell your data producers to slow down so you don't instantly overflow your message queues. You need to aggressively scale mobile chaos testing to deliberately break things in production. You should provide a 45 to 60-second termination grace margin in Kubernetes just so your apps can safely flush their internal buffers before the system actually kills them. And you need to implement the warm escalation. That means proactively paging secondary engineers and subject matter experts early during degraded performance rather than waiting for a total catastrophic failure to hit.
And look, when incidents do happen, because they will for sure, senior teams enforce blameless postmortems using the 5 whys technique. We don't just stop at, oh, the developer pushed a bug. No, we drill down. Why did the reviewer miss it? Why wasn't there an automated test? Why is it so hard to test locally? Because we lack proper test accounts in the development environment.
That right there is how you drill past the illusion of surface-level human error to expose and actually fix the deeply embedded systemic failures that really cause major outages.
Ultimately, technical debt is a silent business killer, so I want to leave you with this question. Are you just shipping code and crossing your fingers that the dashboard stays green, or are you aggressively deleting technical debt, tracking the payload over the plumbing, and engineering for real systemic resilience? The answer dictates whether you're building a system that can scale or a system that will inevitably collapse under its own weight. Think about it. If you want to stop fighting fires and start architecting for the payload, hit subscribe. And hey, let me know in the comments below, which piece of technical debt are you deleting first today?